have another amazing guest and very interesting show for you today. Launch capacity is one of the biggest challenges today, and today's guest and his crew are working on a way to address this limiting factor. Welcome to the Tech and Space Leaders Show, where we learn lessons from leaders of the next frontier. I am your host, Lisa Dreher, and I'm really excited to introduce our guest for today, Rowland Reeves. He is the founder and CEO of U.S. Space Corporation. Welcome to the show, Rowland.
Thank you for having me. It's very, very nice being here. Thank you very much, Lisa.
Absolutely. So maybe we can start by having you give us a little bit of background on yourself and U.S. Space Corporation.
Okay, I'm a retired computer and technology teacher. My co-founder and I have designed a new advanced rocket engine and advanced launch vehicle. Our company is U.S. Space Corporation. Um, we cold pitch our design to the NSF SBI program, and after a very long and rigorous due diligence process. It was really grueling at times. It was tough. We did get awarded a grant to test and build and test our rocket engine. We're a true startup in every sense of the word. I mean, we're just, and I will tell you how much of a startup we are in just a moment. Just a quick description of our story. If this doesn't get too long here, we'll just try to let you know what's going on. In 2017, after several months of investigation into the space industry, my co-founder and I decided that the space industry had some major design, engineering, and concept flaws, major ones. This The results of this is we got very frustrated with what we thought was an immense, huge loss of potential for the industry. So on November 8th, 2017, we decided to create solutions to the problems that we identified. Just like that, two people sitting there and say, hey, well, let's solve this. So that's what we did. Um, Fast forward to 2023, that's 6 years there. Um, After thousands of hours of research, design, and simulations, we filed multiple patents with the USPTO. And then on June 1st, 2023, we cold pitched our engine design to the NSF, which resulted in a formal invite from them to submit a full proposal. We had some major challenges in our application. And this story might be somewhat of an encouragement to anybody that has a new invention concept, because you might think you have a lot of challenges. Well, here's some of the challenges that we had, and we managed to overcome them. First of all, neither of us, myself or my co-founder, had any formal training in the aerospace industry or any experience really. So that's a huge challenge right there. We cold pitched without any connection to any established aerospace space university or aerospace company. Our performance claims for our rocket engine were beyond believable. Even we couldn't believe them, and but we did after the thousands of hundreds of simulations we ran. But cold pitching it just this can't be. I mean, and then finally, we had just started our company. We had no engineers on our staff, and we had no place to test our engine. So those are the challenges we faced.
Oh my goodness.
Yeah, talking about you know starting from 10 feet down and working your way up, right? Uh, the We got a grant from the NSF on September 9th, 2024. Program manager from the NSF simply texted us and just in big capital letters just said, you got it. You got the grant. The next day, the funds were in our account. We later found out that that year in 2024, 50,000 applications were made to the NSF. Of those, only 12,000, excuse me, not 13, 12,000 grants were awarded. So us grantees. We beat out 38,000 other applicants. So it's a
Wow. Oh my
rare,
gosh.
rarefied group. Our program manager at the NSF stated that uh, the rigor of the review that they put us through was beyond belief. She said she had not seen such an in-depth look and such a long look, 9 months, at any application since she had been there. So they really gave us a going over. But she said, this is what the result of that is. Your technology has earned huge credibility with this staff. And she said, the grant money is probably good for you. And I said, yes. But she said, the credibility that this rigorous review gives to your technology will probably in the long run, be worth more than the grant itself. And we have since found that that's true. Um, the the people that reviewed our technology, they're hardcore aerospace engineers with 20, 30 years, every one of them. So they at the end they told her they got it. They've got something here, and it's worth it's worth an investment for us to see what we can do. The concept is totally valid.
Wow, that's amazing. Okay, so let's actually talk about the concept. What were some of the design flaws that you identified, and how are you addressing them?
Uh, the with the engine, we'll talk about that because that's what we got the grant for. The engine, all current rocket engines have a huge problem, and that is the back pressure from the combustion chamber. That is from the rocket engine back up into the pumps that are feeding the rocket engine, and that's accepted as a given in the industry. Well, my co-founder and I didn't accept that. The problem with that back pressure is that it limits the amount of fuel that can be pushed into the combustion chamber in any given second. That's called mass flow rate. And for example, a typical rocket engine will have 325 bar, that's 325 atmospheres of pressure inside the chamber, forcing out. Because the thrust that goes down out of a rocket engine, well, guess what? The same amount of thrust is pumping back up against the engines, against the pumps. So what you have to do is you have to have a pump that has more pressure going into the chamber than the chamber itself is creating. That is a very, very difficult technological challenge.
Yeah.
Current pumps have about a 50 bar differential in pressure. The pumps are pumping in at about 50 bar more than the engine itself is producing, and that gives them good flow. But what we did is we found a way to negate the back pressure. So we have 375 bar of pressure going into our engine from the pumps with very little back pressure. So we're putting in, because we have very little back pressure, all that pressure going in feeds the engine much more fuel per second than is possible through current engines. And that's where we get these huge increases in thrust that our simulations have shown us.
Wow, that's amazing. Okay, so the spacecraft that you're talking about is called the space truck, is that right?
Right. Yeah. It's a space truck. And we've very quickly we've decided that our investigations showed us that um, the current tube shaped rocket engines, rocket ships, tube shape, first stage, second stage, are extremely inefficient. Okay, first of all, they're dead weight lifting um, the entire mass straight up against gravity before they turn and finally go into a horizontal position, which puts them in orbit. That in itself takes a lot of fuel. The second thing is the ships are first stage and second stage. All these engines in the second stage are what we call them lazy engines because they're not being used during the launch. They're just sitting there. So what we designed is a side-by-side system where the first and second stages are side by side. They go up and both the first and second stages engines are uh, being used. There's thrust coming out of them. So basically, you double the thrust that you can get out of the rocket ship by using both the first and second stage engines during the launch. The fuel during launch comes all from the first stage. The first stage breaks off, then the second stage lines now cut in, and the first stage lines break away, and the second stage then goes up to launch. That in itself created a much greater lift capacity for our ship because we're using all of the engines during the launch, which current tube shaped systems do not use. Uh,
Interesting.
yeah,
So you're also looking at launching at kind of a different angle, right? Than the standard, very vertical. So can you
right,
talk about that inclined launch system as well?
right. Vertical launch systems, they're deadlift against gravity straight up. So you're not getting any really orbiting velocity out of that at all. And also you have no wing, you don't have any lift from any wings. And that we felt was a big loss of potential. So if you launch your vehicle an incline, say up on a tilted gantry, or say up the side of a slightly raised hill, you can get a much longer launch uh, run up, and you can also put launch assist systems attached to the rockets, like say on a rail system that goes up the side of the hill. You can put a launch assist vehicle on there, or rockets, or electromagnetic thrusters to help you launch the vehicle. Our vehicles have wings, so when it's launched, and it's now already going somewhat in a horizontal direction. The lift, the vertical lift, is provided by the wings. Okay, not by just dead lifting this up against gravity. So the wings are providing most of the lift of us. Now, of course, when the atmosphere gets thinner and you start getting up there, the wings aren't doing that well. But by then, the atmosphere is so much thinner, and you've been going in a horizontal direction for a while. Your speed and your orbit velocity and the amount of energy you needed to get up there is much less than if you had to deadlift this mass straight up. So we're going to use a somewhat of a inclined runway type system for our launch vehicles.
Oh, that's really fascinating. That's really fascinating. What does that mean from also a recovery standpoint? So when the spacecraft comes back to Earth.
Okay, so we have wings. Our vehicle it can be called a space truck, but it can also probably be called a space plane. Think of the space shuttle if you want an image of it, but it's bigger than the space shuttle, and the wingspan is much larger. Our ships have wings, and it wasn't for the launch initially. We determined that the most difficult part about any flight now, commercial flight, is not the launch. Everybody can do the launch. The tough part is the reentry. But unfortunately, there's this ICBM legacy mentality that says all ships must be, built and designed for launch, optimized for launch, and then after they get them up there, they somehow try to figure out how we get them back down. Well, the reentry and landing is the most tough, is the toughest part of any launch, any flight. And so we felt that that was really backwards and legacy thinking. So we optimized our ship for reentry and landing, and then went back and tried to figure out how to launch it, because the reentry and landing is the toughest part. And sure enough, so we get it we've designed it for reentry and landing. Well, sure enough, now we can also use the wings for the launch, because now you're getting lift off of the wings. So the wings get a double use. Think of it this way. If a 747 tried to go straight up, it couldn't do it. It's the wings that give it the lift, when it takes off. And that's the same with our spaceship. And that's why we have this vehicle, and we think it's going to be much more efficient. It's going to be able to lift much larger volumes and masses of cargo. It's and it also can land because it comes in more like a plane. It can land anywhere. It can land on an area about 2 football fields in size.
Wow, that's amazing. So that's what I was going to ask next
Yeah.
is does the launch process and the landing process require new specialized launch locations, facilities?
The launch facilities, we will have to have inclined gantries or rails up the sides of a low rising hill or something like that. So the launch will have to have, there'll have to be more infrastructure for that. But just pricing that out, we didn't find that to be too much more expensive than the current vertical launch towers and all the everything they have to put in with those. And also, you have on the vertical launch towers, they have to be up on this mound so that you have the splashways for the thrust. Where when we're on the incline, the thrust is going to come straight out the back, just like a regular airplane taking off. So for takeoff, we will need some different type of launch structures, but not the expense. We don't think is going to be much more than a vertical tower. The landing is anywhere. We can come in and we flare, and then we come down, and we do have some propulsive rotating rockets that come down, and we can land literally on an area the size of a football field. Anywhere around the world, we can do point to point on the Earth very simply, and we can land in slightly inclined surfaces on sandy soil. We can land anywhere. So
Wow,
yeah.
that's amazing. Okay, so where are you in the development process? When might we see a first test launch, for example?
Our development process right now, let's see, that's our milestones. Okay. Our coming milestones right now is we are hot fire testing the prototype engine right now. We have, in fact, we just ordered all the engine parts. They have to be cleaned and made oxygen ready. That's because, believe it or not, stainless steel under high pressure oxygen will actually burn if it has any impurities in it. So the parts are being sent out to be cleaned. They come back. We'll finish assembling the engine, and we'll be testing our prototype the end of May and probably through June. After that, we're going to go through phase 2 funding with the NSF. We're building out a much larger sized engine. And then, of course, after that, and cash flow comes in, and we start getting partnerships, we'll do a prototype of our launch vehicle and start, working up from there. So we do have these milestones all lined up. We do have dates for them, and we are moving along. It's, of course, for a startup, it's not moving as fast as we'd like to, but that's where we are right now.
Wow, very exciting. Now, you even have a bigger vision that goes beyond launch, and that includes space based real estate and artificial gravity habitats. Can you talk a little bit about your even broader vision?
Right. We are going to be a vertically integrated company. Well, let's put it this way: we and our partnership companies, because we're going to be very big on licensing and partnerships, and because we want the technology, we feel the technology is much more advanced than what's out there. We want the technology to be infused into the industry as quickly as possible, and what that means is that we're going to increase the lift capacity to low Earth orbit, and this is going to enable us to build artificial gravity orbiting facilities around the Earth, Mars, Moon, around the solar system, and they're going to be way cheaper than trying to maintain a moon colony or a Mars colony. And we can build them right here in low Earth orbit, and then we could move them over to the Mars or over to the moon, and they can go around. So people living in these colonies can go down and work a month or two on the moon, and then they can come back up, and they've got artificial Earth-sized gravity. They are protected from meteorites. It's pressurized. They're going to be O'Neill-style orbiting cylinders, so they can grow their own food. So that's our vision. We have an engine, a launch vehicle, and orbiting artificial gravity colonies, basically.
One of the things that you said just made me think, how does your launch system impact payload capacity?
Oh, okay. Because we've well, two reasons. It impacts it immensely. Two reasons: because of our launch, our takeoff system, where we have both the first and second stage engines working at the launch, that increases cargo capacity. The second thing that increases cargo capacity and is the 62% increase in thrust and 40% increase in efficiency that our engines provide. And these claims by us is what really stumped the hardcore aerospace engineers at the NSF when they first looked at our. But when we explained the system to them, and how we have negated the back pressure and how much more fuel can go through the engines, it became apparent that perhaps we're even a little bit underestimating what the increase in thrust is. So that's where we're going to be lifting the cargo mass. It's going to be twice as our cargo mass and volumes are going to be twice what even the most advanced engines are today, and I mean launch vehicles are today. So we're quite excited about it, and people that our engineers and engineers we've shown this to are quite excited also.
Wow, amazing. Okay, so I want to end with one last question, and that is really about a more general view of the future. What major developments and changes do you see in the aerospace industry coming in the future?
Right. We see some significant changes coming up. First of all, there's going to be an evolution to what away from these legacy ICBM tube type ships to more what you would call space plane designs, where they're taking off horizontally or maybe at an incline, and they're landing more like planes. And in fact, when the first one of those space planes that does that, that is going to spell the end of the tube launch systems almost immediately. Because when you can land anywhere and you can use a runway or just a modified incline, that's going to end that. So we feel that that's going to change. There's going to be a massive increase in launch to orbit capabilities for spaceships. That's another thing. There's going to be a shift in emphasis from Moon and Mars colonies to artificial gravity facilities. You can build multiple artificial gravity facilities compared to building even one or two Mars-based or Moon-based, facilities. So they're cheaper and they're everywhere. Um, Moon and Mars have limited enterprise potential. Um, just think of this: you have dozens of artificial gravity structures orbiting around, theme parks, foundations and platforms for astronomy, telescopes, orbiting factories, retirement villages in space. It just goes on and on and on.
Wow, amazing. Oh my gosh. Okay, so Roland, I really want to thank you for making time to be here today. If someone wants to learn more about US Space Corporation, what should they do?
They can catch us at usspacecorporation.com. That's our email. They could also look at our website, which is still in the development stage, but it does give all the basics. Just some of the buttons aren't active, but at https at usspace.space. That's our website. Let's see. Also, you can catch us at US Space LinkedIn, and for all our latest developments and blogs and that type of thing.
Excellent. Well, thank you so much for making time to be here today. We really appreciate it.
Yeah, it was fun.
Great. And I do want to take a moment to thank GuideForce for hosting these sessions. To learn more about GuideForce, you can visit guideforce.com. And we'll see you next time on the Tech and Space Leaders Show.
Thank you very much.